Welcome to Advanced Problem Solving. Today we are tackling real-world coding challenges that test everything you've learned. These problems combine multiple concepts: data structures, algorithms, object-oriented programming, and Python best practices. Get ready to think critically, design solutions, and write professional code. Let's dive into the challenge. Problem solving is the core skill of programming. It's not just about knowing syntax. It's about breaking down complex problems, designing algorithms, and implementing elegant solutions. Today's challenges will test your ability to think algorithmically and write clean, efficient code. Follow these 4 steps for every problem. First, understand the problem thoroughly. Read carefully. Identify inputs and expected outputs. Consider edge cases. Second, plan your approach. Choose appropriate data structures and algorithms. Third, implement your solution with clean, readable code. Fourth, test thoroughly and optimize if needed. This systematic approach leads to better solutions. Challenge 1. Build a complete inventory management system. This real-world problem requires object-oriented design, data validation, and business logic implementation. Create a product class with name, price, quantity, and category. Build an inventory class that can add, remove, and search products. Implement methods to calculate total inventory value. Find low stock items below a threshold, and generate reports by category. Handle errors like negative prices and invalid quantities. For bonus points, implement multi-criteria product search. This tests OOP, validation, and data management skills. Before coding, let's design our solution. Good design makes implementation easier and code more maintainable. We'll create 2 main classes. Product stores individual product data and provides methods to update quantity and calculate value. Inventory manages a collection of products using a dictionary for fast lookup. It provides methods to add, remove, search products, and generate reports. The inventory class uses product objects, creating a HASE relationship. This design is clean, modular, and extensible. Let's implement the product class with validation and proper encapsulation. The product class validates inputs in __init__, ensuring prices and quantities aren't negative. Update _quantity accepts positive or negative amounts for adding or removing stock, with validation to prevent negative inventory. Get _value calculates total value by multiplying price by quantity. _str__ provides readable output. _repr__ shows constructor form. This is a complete, professional product implementation. Now let's implement the inventory class with comprehensive product management features. Inventory uses a dictionary to store products with unique IDs for fast lookup. Add _product creates a product instance, assigns an auto-incremented ID, and stores it. Remove _product validates the ID exists before deletion, raising a clear error if not found. This provides robust product management. Search _by_ name uses dictionary comprehension to find products with case-insensitive matching. Get _total_ value sums values from all products efficiently. Find _low_ stock returns products below a threshold with a default of 10. Get _report _by_ category groups products by category for reporting. These methods provide comprehensive inventory analysis capabilities. Let's see our inventory system in action with realistic usage examples. We create an inventory and add various products with different categories. Update stock by selling items. Calculate total inventory value across all products. Find low stock items needing reorder. Search products by name with partial matching. Generate category reports for organization. This demonstrates a complete, functional inventory management system handling real business operations. Challenge 2. Build an advanced text analyzer that provides comprehensive statistics and insights about text data. This tests string processing, algorithms, and data analysis skills. Build a comprehensive text analyzer. Count characters, words, sentences, and paragraphs. Calculate average word and sentence lengths for readability analysis. Find most common words while filtering out stop words like the and a. Implement Flesch-Kincaid reading difficulty scoring. Add basic sentiment analysis by counting positive and negative words. Generate word frequency data for visualization. Bonus. Detect repeated phrases for style analysis. This combines string processing, statistics, and algorithms. Let's break down the text analyzer into logical components. Modular design makes complex problems manageable. We organize the analyzer into 3 modules. Basic statistics handles counting operations. Characters, words, sentences, and paragraphs. Advanced metrics calculates averages, reading difficulty scores, and finds common words. Sentiment analysis examines emotional tone and generates frequency data. This modular structure keeps code organized and testable. Let's implement the basic text statistics with proper text processing. The text analyzer initializes by processing text into sentences, words, and paragraphs. Split sentences uses regex to split on punctuation. Extract words finds alphanumeric words, converting to lowercase for consistency. Split paragraphs divides on double new lines. Count methods return lengths of these processed collections. Processing once during initialization makes subsequent operations efficient. Now let's implement advanced analysis including readability scoring and common word detection. Average word length and average sentence length calculate basic readability metrics. Common words uses counter to find frequent words, optionally excluding stop words for meaningful results. Reading difficulty implements the Flesch reading ease formula, which combines sentence length and syllable count to score text difficulty from 0 to 100. Higher scores mean easier reading. Count syllables provides approximate syllable counting by identifying vowel groups. Finally, let's add sentiment analysis to detect emotional tone in the text. Analyze sentiment maintains lists of positive and negative words. It counts occurrences in the text and calculates a sentiment score from -1 to +1. The score determines overall sentiment as positive, negative, or neutral with a threshold of 0.2. The method returns comprehensive sentiment data including the classification, score, and word counts. Word frequencies provides raw frequency data for visualization or further analysis. Let's analyze real text and see all our metrics in action. We analyze a sample text about Python. Get basic counts of characters, words, and sentences. Calculate readability metrics like average word length and Flesch reading difficulty score. Find the most common meaningful words. Perform sentiment analysis detecting positive and negative words. This comprehensive analysis provides insights into text complexity, content, and emotional tone. The analyzer handles real-world text processing challenges professionally. Challenge 3. Implement the least recently used cache. A classic data structures problem used in operating systems, databases, and web applications. This tests your understanding of hash tables, linked lists, and algorithm efficiency. The LRU cache maintains a fixed capacity. When you get or put an item, it becomes the most recently used. When the cache is full and you add a new item, the least recently used item is evicted. Both get and put must run in O(1) constant time. This requires combining a hash table for fast lookup with a doubly linked list for tracking access. Order. This is a classic problem asked at Google, Amazon, and Facebook interviews. Let's understand LRU cache behavior before implementing it. Watch how LRU cache works. We add A, B, C in order. When we access A with get, it moves to the front as most recently used. When we add D and the cache is full, B is evicted because it's least recently used. The front of the list always has the most recent item. The back has the least recent. This ordering is maintained automatically by the data structure. Python's ordered dict makes LRU cache implementation elegant. It combines hash table and linked list internally. Ordered dict maintains insertion order and provides move_to_end for reordering. Get checks if key exists, moves it to end marking it as most recent, and returns the value. Put checks if key exists. If so, updates value and moves to end. If new and cache is full, pop item with last equals false removes the first, least recent item, then adds the new item at the end. Both operations are O(1). Thanks to OrderEdict's implementation, this is a clean, efficient LRU cache using Python's standard library. Let's see the LRU cache in action with various operations. We create a cache with capacity 3 and add items A, B, C. Accessing A moves it to most recent. Adding D when full evicts B, the least recent. Getting evicted B returns none. Updating A moves it to most recent again. The practical example shows caching expensive function results. First calls compute results. Subsequent calls retrieve from cache. This dramatically improves performance by avoiding redundant computations. LRU caches are fundamental in real-world systems. Challenge 4. Given a list of time intervals, merge all overlapping intervals. This classic algorithm problem appears in scheduling, calendar applications, and resource allocation systems. Merge intervals takes a list of interval tuples representing start and end times. Intervals 1 to 3 and 2 to 6 overlap because 2 is between 1 and 3. They merge into 1 to 6. 8 to 10 and 15 to 18 don't overlap with anything, so they remain separate. The algorithm must handle all overlapping cases efficiently. Target O(n log n), time complexity and return sorted merged intervals. This appears in meeting room scheduling and calendar applications. Let's visualize how interval merging works step by step. First, sort intervals by start time. Begin with the first interval, 1, 3, as current. Check if next interval, 2, 6, overlaps. Start 2 is less than or equal to end 3. So yes, merge them into 1, 6, taking maximum end. Check next interval, 8, 10. Start 8 is greater than end 6. So no overlap. Add 1, 6 to results and start fresh with 8, 10. Continue until all intervals processed. The algorithm efficiently merges overlapping intervals in a single pass after sorting. Let's implement the merge intervals algorithm cleanly and efficiently. The algorithm first handles empty input. Sort intervals by start time using a lambda function. Initialize results with the first interval. For each remaining interval, check if it overlaps with the last merged interval. If current start is less than or equal to last end, they overlap. Merge by extending last end to the maximum of both ends. If no overlap, add current as a new separate interval. Time complexity is O, n log n. From sorting, space is O, n. For results, the test suite validates various cases. Basic overlap, multiple overlaps, no overlaps, contained intervals, and unsorted input. Let's apply interval merging to a practical meeting scheduler that finds available time slots. Meeting scheduler manages meetings within work hours, defaulting to 9 a.m. to 5 p.m. Add_meeting validates times are within work hours and automatically merges overlapping meetings. Using our interval algorithm, find_available_slots searches for gaps of specified duration. It checks before first meeting, between all meetings, and after last meeting. This real application demonstrates how algorithm knowledge solves practical problems the scheduler could power calendar applications, conference room booking systems, or resource allocation tools. Let's review key strategies that helped us solve these complex problems these techniques apply to any programming challenge you'll face. First, break down complex problems into manageable sub-problems, solve each independently. Then combine solutions. Second, choose appropriate data structures. Dictionaries for fast lookup, lists for ordered collections, sets for uniqueness. Third, always consider edge cases, empty inputs, single items, invalid data, boundary conditions. Test these explicitly. Fourth, optimize after achieving correctness. Make it work first, then make it fast profile to find actual bottlenecks before optimizing. Let's recap the essential lessons from today's advanced problem-solving session. We learned object-oriented design for modeling real systems with proper encapsulation and validation. Algorithm selection based on complexity requirements. Choosing O1. Operations when speed matters. Data structure mastery. Understanding when to use dictionaries, lists, sets, and specialized structures like ordered dict. Code quality. Writing clean, tested, well-documented professional code that others can maintain. Real-world application. Taking theoretical algorithms and applying them to practical business problems like inventory management, text analysis, caching, and scheduling. Now it's your turn. Here are additional challenges to sharpen your problem-solving skills. Challenge A. Build a complete banking system with accounts, transactions, and interest calculations. Challenge B. Implement graph algorithms including breadth-first search, depth-first search, and shortest path finding. Challenge C. Create a task scheduler with priority queues handling dependencies between tasks. Challenge D. Implement classic design patterns like singleton, factory, and observer in practical scenarios. Start with easier challenges and work up to harder ones. Practice is key to mastering problem solving. Finally, here are proven strategies for becoming an expert problem solver. Practice daily. Consistency beats intensity. Solve at least one problem every day to build momentum. Learn from others. Read different solutions to see alternative approaches and techniques. Explain your solutions. Teaching forces you to understand deeply. Study complexity. Analyze big O notation to write efficient code. Build projects. Apply skills to real applications, not just coding exercises. Join communities, participate in forums, competitions, and open source projects. These habits transform good programmers into exceptional problem solvers. Congratulations! You've completed advanced problem solving. You now have skills to design complex object-oriented systems. Choose optimal algorithms and data structures. Solve real-world coding challenges. Write professional efficient code. And think algorithmically. But this is just the beginning. The journey from good to great is paved with practice. Keep solving problems, building projects, and learning new techniques. Every challenge you overcome makes you a better programmer. The skills you've learned today will serve you throughout your career. Now go forth and build amazing things. Thank you for joining this advanced problem-solving journey. Happy coding!